Dear students, in last class we designed a linear phase FIR low pass filter using rectangular window. Today I will take up a problem on designing a linear phase FIR high pass filter using Hamming window with a cutoff frequency omega c equal to 0.8 pi radians per sample and n equal to 7. Solution: given desired frequency response HD of e raised to j omega equal to e raised to minus j alpha omega for omega greater than or equal to minus pi less than or equal to 0.8 pi with minus sign, and omega greater than or equal to plus 0.8 pi and less than or equal to plus pi equal to 0 otherwise. This frequency response may be shown graphically in this way. Magnitude of HD of e raised to j omega from minus omega c to 0 and 0 to omega c is equal to 0 here, and that is what we have written here. For linear phase, h of n minus 1 minus n is equal to h of n. The desired impulse response HD of n is obtained by taking inverse Fourier transform of HD of e raised to j omega. So HD of n is equal to 1 by 2 pi integration of HD of e raised to j omega into e raised to j omega n d omega with the limits minus pi to minus omega c plus integration of hd of e raised to j omega into e raised to j omega n d omega with limits of integration omega c to plus pi. One by 2 pi into the bracket minus pi to minus omega c. hd of e raised to j omega is e raised to minus j alpha omega into e raised to j omega n d omega plus integration from omega c to pi e raised to minus j alpha omega into e raised to j omega n d omega. That is equal to 1 by 2 pi integration between the limits pi to minus omega c of e raised to j omega into the bracket n minus alpha d omega plus integration with limits omega c to pi. Here I have to make it minus, please correct it, e raised to j omega into the bracket n minus alpha d omega. Integrating and simplifying, we get 1 by 2 pi e raised to j omega n minus alpha by j into n minus alpha limits of integration are from minus pi to minus omega c, so I have to take the same limits here, plus e raised to j omega into the bracket n minus alpha by j into the bracket n minus alpha here the limits of integration were omega c to pi, therefore we will write lower limit as omega c and upper limit as pi. Now substituting in place of omega the value of minus omega c minus pi, and here in place of omega pi and omega c. 1 by 2 pi e raised to minus j omega c into the bracket n minus alpha by j into n minus alpha minus e raised to minus j pi n minus alpha by j n minus alpha plus e raised to pi into the bracket n minus alpha divided by j into n minus alpha minus e raised to j omega c into n minus alpha by j into n minus alpha. Taking n minus alpha common outside and 2 inside the bracket and then rearranging the terms, we get e raised to j pi into n minus alpha minus e raised to minus j pi into n minus alpha minus e raised to j omega c into n minus alpha minus e raised to minus j omega c into n minus alpha by 2j. One upon pi into the bracket n minus alpha into. Now we will write this as sine of pi into the bracket n minus alpha minus sine of omega c into the bracket n minus alpha. If we take pi into n minus alpha in the denominator inside the bracket, then we get it as sine of pi into n minus alpha by pi into n minus alpha minus sine of omega c into n minus alpha by pi into the bracket n minus alpha. This HD of n is valid for all n values except n equal to alpha. So I'll write here for all n except for n equal to alpha. Since capital N is given as seven, n minus 1 by 2 is 7 minus 1 by 2, that is equal to 3, and n minus 1 is equal to 6. And we know that alpha equal to n minus 1 by 2, and now that is equal to 3. So for n equal to 3, that is alpha, HD of n obtained above becomes infinity. So to get the value of HD of n for n equal to alpha, we have to go to the initial step, that is we have to take HD of n equal to 1 by 2 pi integration from minus pi to minus omega c e raised to j omega into the bracket n minus alpha d omega plus omega c to pi integration of e raised to j omega into bracket n minus alpha d omega at n equal to alpha. That is 1 by 2 pi If I put n equal to alpha, it will become 0 here. E raised to 0 is 1. So integration of d omega is omega. Limits of integration are from minus pi to minus omega c, and here also integration of e raised to j omega into n minus alpha is omega, but limits of integration are plus omega c to pi. Substituting, we get 1 by 2 pi minus omega c, minus of minus pi will become plus pi minus omega c. That is 1 by 2 pi minus 2 omega c plus 2 pi. Taking 2 common outside, we get pi minus omega c into 2 by 2 pi. Cancelling 2 and 2, we get pi minus omega c upon pi, or 1 minus omega c by pi. That is 1 minus omega c value is given to us as 0.8 pi. .8 pi upon pi, pi and pi will cancel. We get HD of 3 equal to 1 minus 0.8, that is 0.2. Next we will calculate Hamming window sequence. That is WH of n equal to 0.54 plus 0.46 into cos of 2 pi n by capital N minus 1 for n equal to minus capital N minus 1 by 2 plus capital N minus 1 by 2 and equal to 0 otherwise. So here n value varies from minus 3 to plus 3, that is minus 3, minus 2, minus 1, 0, 1, 2 and 3. So WH of minus 3 equal to 0.54 plus 0.46 into cos of 2 into pi into minus 3 upon 6 into 180 by pi, that is equal to 0.54 plus 0.46 into cos of minus 180. Simplifying, we get WH of minus 3 equal to 0.08. Similarly, we have to calculate WH of minus 2 to WH of 3. So WH of minus 2, WH of minus 1, WH of 0, WH of 1, WH of 2 and WH of 3. One calculation I have shown here in detailed. Next calculation you have to do on your own. I will just give you the values here. 0.31, 0.77, 1.0, 0.77, 0.31, 0.08. About WH of 0, you can see here the symmetry. Now we will calculate desired impulse response HD of n for n equal to 0 to 6. Next, right here, calculation of HD of n for n equal to 0 to 6. HD of 0 is equal to sine of pi into, in place of n we have to put 0, in place of alpha we have to put 3 minus sine of omega c. Omega c is 0.8 into pi, inside the bracket 0 minus 3. Pi into n minus alpha is denominator for both the terms here. Convert sine of angle in radians here into degrees, and here also keep the denominator pi in radians only and simplify. You will get 0 here because sine of angles which are integer multiples of 180 gives us 0 minus 0.1009. So you get HD of 0 as 0.1009 with negative sign. Similarly, we have to calculate HD of 1, HD of 2, HD of 3 we have already calculated. So HD of 1 is equal to 0.1514 and HD of 2 is equal to minus 0.1871. Using symmetry property, of HD of n. Now we can write HD of 0 equal to HD of 6, that is equal to minus 0.1009. HD of 1 equal to HD of 5, that is equal to 0.1514. HD of 2 equal to HD of 4, that is equal to minus 0.1871, and we have calculated HD of 3 as 0.2. Now I will write WH of n and HD of n one below the other. WH of n is minus 0.08, 0.31, 0.77, and then 1, 0.77, 0.31, 0.08 with minus sign, and its 0 is now here. That is 0th sample 1 is here. The 0th sample of WH of n is 1, and that can be shown here. Next, HD of n I will write. Minus 0.1009, 0.1514, minus 0.1871, 0.2, minus 0.1871, 0.1514, and minus 0.1009. For HD of n, 0th sample is minus 0.1009. Before we multiply WH of n and HD of n, we will write these two sequences in such a way that minus 0.08 and minus 0.1009 are one below the other. 0.31 and 0.1514 are one below the other, and so on. That is, in this way. Writing like this is as good as multiplying WH of n by z raised to minus of n minus 1 by 2, that is minus 3. Now we have to obtain impulse response H of n of linear phase high-pass FIR filter. So right here, obtaining H of n equal to WH of n into HD of n. Here we have to multiply sample by sample. So that will be equal to minus 0.0081, zero point 0469, minus 0.1441, 1, minus 0.1441, 0.0469, and minus 0.0081. Taking Z transform of H of n, we get H of Z, that is Z transform of H of n. After taking Z transform, rearranging the terms, we get H of Z equal to minus 0.0081 into 1 plus Z raised to minus 6, because the 0th sample and 6th sample are equal to 0.0081 with negative sign. Similarly, 0.0469 into Z raised to minus 1 plus Z raised to minus 5 plus 0.1441 with negative sign into Z raised to minus 2 plus Z raised to minus 4 minus 0.2 into Z raised to minus 3. So this is the digital transfer function of high pass linear phase FIR filter. Dear students, in next class I will be taking a problem on design of a linear phase FIR bandpass filter using Hanning window. Now I will stop the class. Thank you.